Hello, everyone. So, welcome to our review. Let me check my audio levels before I start because the last thing I need is to spend 2 hours talking into a microphone and then there's no sound afterwards. And it looks good. It sounds good. Okay. There's no one in the chat right now, which is fine. I'll look at the chat every once in a while, anyhow, to see if people have joined since then. But you could. That's the whole point of doing a live stream rather than something like a Zoom call, because it's recorded and you can watch it later. Okay. Before I jump in, what's on the test? And it's all the material since the last test. Okay, and the last test we kind of cut it at a strange place. It was between the encoding, which was part of the last test, and the data sizes and rates, which is part of this test. The two are related to one another, and it just turned out because of other scheduling things that I had to break it up that way. But it would have been better to put those two together. Nonetheless, there's a little bit from the data encoding that has to carry over into the data sizes and rates problems. Okay, so that's the first thing: data sizes and rates, and that's the name of the topic in Canvas. Okay, and the second thing that we did was we talked about operating systems. Okay, we talked a little bit about software in general. I got to come back to software after the test, but we talked about software, but in particular about operating systems and what operating systems do for you. Okay, and then we talked about the internet. All right, and for all of these topics, what I do is I think to myself, what is the kind of information that you would need far into the future? That will help you to understand this technology, because it's a continuously evolving technology. And so if I don't dig a little bit into beneath the surface, the course would be kind of useless, because everything that I tell you would kind of disappear. But the stuff that I've taught you has been here for many years, okay, and it'll be here for many more years. Okay, so that was the philosophy behind this material. All right, well let's start. So what are data sizes and rates problems? What are they all about? So there were problems, okay. And students sometimes find word problems difficult, but if you keep practicing them, um, you know, you'll get better at it. Okay, so don't get discouraged. And what do they have? What kinds of subject do they treat with? What kind of subject do they treat? Okay, the first, when we talk about data sizes, we can make estimates on the sizes of files. All right, so like a file, that icon that's like a Word file. You double click it, it opens up in Microsoft Word. Those kind of things. Those are files, and they take up space on your hard drive and so on. And you also transmit them over the internet. And so it's good to know how big these things are and how much you can fit on various devices. Okay, so that's the size problems, and the other one are the rates problems, which are like transmission over the internet. Okay, especially with the rate problems, I would say, look, if you're in the medical field, you deal with rate problems all the time, because you talk about rates at which medicines are ingested and used by the body, drip rates when it comes to like intravenous, all these sorts of things. So rates come up everywhere. Even though I'm teaching you rates in the context of computers and the transmission of information, it's really worth learning how to think about rate problems, because they're, like I said, literally everywhere. Okay, well, let's start. All right, so the first thing you should know about is this chart right here. And this chart, it is an open book test, so you don't have to memorize this chart, but you do have to know where it is in the web page, okay, in my summary notes. And it just gives you an idea of approximately how big various files are. Okay, so an image, a low quality image, like the kind of image that you would get on the internet, is about 100 kilobytes per image. Okay, they can certainly be a lot bigger than that, but that's kind of like the size of the images on the internet. Okay, low quality. A movie of a decent quality, that's like DVD quality. Okay, movie. I know we don't carry around DVDs anymore, but they're still around, and we still have DVD quality. And one movie, which is about 2 hours, is about 4 gigabytes. Okay, and audio is like music or whatever, or if you record a lecture. For every minute of recording, you need about 1 megabyte of storage. Okay, and then finally documents, and the documents vary a bit more, because it depends what kind of document you're talking about. And the lowest level document is like a plain text. Okay, ASCII, it's what the ASCII that we studied earlier. So if you have something which is ASCII, one page of ASCII is only like 1.5 kilobytes. Okay, if you're doing Word, one page is 10 times bigger. It's 15 kilobytes. And you say, why is it so much bigger? Because there's font and other information in there. And then finally PDF, and PDF varies a lot. So this is a little bit on the higher end, but generally PDF is like almost at the level of image quality. So every page is almost like a picture. And so it's not surprising that, your web quality images are 100 kilobytes and one page of a PDF is about 100 kilobytes. Okay, the other thing you need to know is how to convert between bytes, kilobytes, megabytes, gigabytes, and terabytes, and petabytes. Okay, and basically every time you go up a level, it takes 1,000 of the smaller units to get the bigger unit. Okay, so it takes 1,000 bytes to make a kilobyte. It takes 1,000 kilobytes to make a megabyte, 1,000 megabytes to make a gigabyte, and so on. Okay. And that chart is also in the notes, okay? And you would have access to that during the test. All right, let's do some problems, okay? So the first problem is approximately how big is a 50-page paper in Word format? Well, this should be straightforward. You say to yourself, well, how big is one page? And then you have 50 of them, so you multiply by 50, okay? So you could say, the size is going to equal what? 50 pages, and each page is... Take a look up here. So you have to look, what kind of format is it? It's Word format, okay? And so Word format is 15 kilobytes a page. And so you would multiply that by 15 kilobytes like that, okay? And I didn't do these problems beforehand, so I don't have the answers. I'm just going to do them on my calculator very quickly. So you just do 50 times 15, and the answer is 750. Okay, good. All right, so there you go. It's 750 kilobytes. Okay, and that answers the first one. All right, so there's a problem like that on the test. I tell you, like, give you a description of some file, and you have to basically calculate the size of the file based on how big each of the individual units are. Okay, so approximately how big is a recording of 13 lectures, each lecture being 3 hours? Okay, so let's think about this a minute. Like, it's 13 lectures. It could be like my course. There'll be like roughly 13 lectures in it. Each lecture is roughly 3 hours. It's usually less than that, but say 3 hours. And you go, well, now how does that work? Okay, so the amount of time, or the size, is going to be 13 lectures multiplied by 3 hours. Okay, but that just does the time. Okay, so let's do that first. All right, so 13 times 3 is 36, right? No, sorry, 39. 39 hours. So we're talking about 39 hours in total. Okay. Now, if you take a look at that chart, you say, well, what are we talking about here? So this is a recording of a lecture. Okay. On a test, I'd be clear, not a video recording, but a audio recording. Okay, so it's 1 megabyte per minute, 1 megabyte per minute. Now you take a look down here and you say to yourself, that's 39 hours. That's not in minutes, okay? But how many minutes are in an hour? So what we can do here is we can do, well, 1 hour is 60 minutes. So 60 minutes divided by 1 hour, like that, okay? So I'm using one of those conversion fractions. Okay, and the way you use a conversion fraction is, remember, the thing that's highlighted there, that fraction that's highlighted there, has to equal 1, and so the numerator and the denominator have to equal one another. So 1 hour is equal to 60 minutes. Okay, the only question is, which do you put on top and which do you put on the bottom? And you want to get rid of the hours, so we'll put the hours on the bottom here like that. So the hours will cancel and you get minutes. Okay, if you put it the other way, then they wouldn't cancel. And so what's that equal to? Well, let me do that on, so it's 39 times 60, and that gives me this many minutes. Okay, so now we have the size in minutes, and that's not what we want. We want the size in bytes. Okay, and now take a look at that chart, and it's pretty easy because 1 minute is equal to 1 megabyte. Okay, and so over here, if you have that many minutes, that's going to equal that many megabytes. All right. Okay, so once again, each minute takes 1 megabyte. That's what this chart says. Each minute of audio takes 1 megabyte. Okay, and we have 2,340 minutes, so that's 2,340 megabytes. Each minute, would eat up 1 megabyte of your storage device. Okay. Now, you wouldn't see that answer on the test. Let me actually put that on the next line here. You wouldn't see the answer quite like that. Okay. And you say, why? So the rule is you have to convert the metric prefix such that the number is bigger than 1 and less than 1,000. Okay, and that's what the metric prefixes are for. They're kind of there to make the number easy to read. Okay, and so you say, well, what can I convert that to? So remember, the next bigger one than a megabyte is, you take a look at the chart here, is a gigabyte. 1,000 megabytes is 1 gigabyte. Okay, so keep that in mind. All right, 1,000 megabytes is a gigabyte, and we have 2,300 megabytes, so that's 2.34 gigabytes. Okay, now if you see that right away, you could just do that. You could just say, okay, that's obvious. It's 2.34 gigabytes. Okay, and you realize that because if you divide by 1,000, you move the decimal over 3 like that. Okay, but if you really need to, you can make that fraction again. Okay, so just for practice, let's make the fraction. And the fraction is the numerator and denominator have to be equal. Okay, and you want to get rid of megabytes. So we're going to put megabytes in the denominator here. And we're going to go to the next bigger unit, which is gigabytes here like that. Okay, and you say, well, I need a number there and there such that this whole thing is equal to 1. Okay, so if you just write the units in there, that's not equal to 1, and so it's not going to work. So you take a look up here and you go, okay, well, let's see, it's 1 gigabyte is 1,000 megabytes, so the numerator needs to be 1 gigabyte and the denominator needs to be 1,000 megabytes. So over here, 1 gigabyte is 1,000 megabytes like that. Okay, and here we go. Well, let me just highlight the fraction. Okay, that fraction there is equal to 1. Okay, and it's effectively like dividing by 1,000. Okay, so the megabyte here divides the megabyte there, leaving you with a gigabyte. Okay, and then the 2,340 divided by 1,000 is 2.34. Okay, and so the test is multiple choice, just like your assignments in the previous test, and that's the answer you would see there. So you have to match that answer. Okay, all right. Let's go on. All right. So how many movies, DVD quality, can you fit onto a 2 terabyte drive? Okay, so this is the number that you can fit, and if you remember how that worked, it was the size of the device divided by the size of one file. Because the way you should think about this is kind of like cutting up a pie. The whole drive is the whole pie, and you want to see how many slices of 4 gigabytes can you get out of that 2 terabyte. Okay, so the device is 2 terabytes. All right, let's do that. Size of the device is 2 terabytes, and the size of one file, you say, well, what file are we talking about here? It's a movie, and you go back up to that chart and you go, a movie video 4 gigabytes. Okay, so and again, approximation. All right, all of these questions are approximations. So over here we're going to say 4 gigabytes like that. Okay, and you take a look at this and you're comparing apples and oranges because the numerator is terabytes, the denominator is gigabytes. Okay, and so you go, oh, well, I got to do something here. Okay, to fix that, to make sure that the numerator and denominator are in the same units. Now, you could do the fraction. I'm going to show you a different way to do it. It might help. Okay, you could take this whole thing like that and you could say, you know what, I'm going to take that terabyte and I'm going to replace it by something. I'm going to replace 1 terabyte by 1,000 gigabytes because they're equal, right? So wherever you see the terabyte, wherever you see TB, you can replace it by 1,000 gigabytes. So over here, where I had TB, I can replace that with 1,000 gigabytes like that. Okay. So there we go. That's another way to do it. Okay, I mean, now that I've shown you the fraction, that unit fraction, where you can't go wrong with that. If you get good at it, then I think you can save yourself a step and do this. Okay, so now you'll see that in the numerator you have gigabytes, in the denominator you have gigabytes, so they'll cancel, and so on top you're just going to get 2 times 1,000 divided by 4, and the gigabytes have canceled, and then you could just do this on your calculator because it's 2,000 divided by 4, and that's equal to, I can do that in my head, 500, and okay, there's your answer. All right, let me put them on different lines so you can see it a little bit better. Okay, so So there you go. That answers it. You can fit 500 movies on a 2 terabyte drive. Okay, and if you remember, 2 terabyte drives are not that expensive. You know, like the old SATA drives, a couple $100, maybe less, $150 easily. You could buy a 2 terabyte drive. Okay, the newer solid states would cost more, but you know, for this, I wouldn't buy a solid state. I'd buy a solid state to put the operating system on, because that this way would boot up faster and run faster. But you know, for movies, I would just store them on something which is a little bit slower but bigger and cheaper. Okay, anyhow. All right, so how many movies can you fit on a 2 terabyte drive? About 500. Okay. And how many movies could you fit on that 2 terabyte drive if only 15% of it is free? Okay, now you could just multiply that 500 by 15%, and that would do it. But let me do it from scratch, you know, just to show you, you know, if we didn't do the previous question, how would you do it? So it's this formula, but with a bit of a modification. Okay, and what's the modification? It's not the size of the device. Okay, it's the size of the free space on the device. Okay, so let's say that size of free space on device. Okay, and you go, well, how do I calculate that? All right, well, the way you would do that is it's the whole thing is 2 terabytes. Okay, but only 15% of it is free. Okay, that's covered. Hold on here. Let me scroll down. Okay, only 15% of it is free. Okay, so you want to do 15% multiplied by 2 terabytes. And you say, well, how do I do that? So you don't multiply by 15, you multiply by 0.15. Okay, and there you go. Okay, so this is how much free space is on the device. Okay, and then you divide that by the size of one file, and the size of one file, it's the same thing. It's a movie. Each one file is just a movie, and so now you get this. Okay, and at this point you go, well, now what do I do? Well, you're still going to be in this position where you have terabytes and gigabytes. So how about we do the same trick again? Replace that terabyte by 1,000 gigabytes, like that. Okay, and we could do a little multiplication symbol in there like this. Okay. All right, so there you go, 1,000 gigabytes, and then multiplied by 0.15 divided by 4 gigabytes, like that. Okay, so let's see, there's the 2 there. That terabyte I replaced by its equivalent 1,000 gigabytes. Okay, and 0.15, there's 0.15, they're like that. Whoops, forgot to close the bracket, and then divided by 4. And let me quickly tell you what that's going to equal. 1 second here. 0.15, 75. Okay, so now we would only be able to fit 75 movies. Okay, when it was completely free, we could fit 500, but you know, there's only 15% free, so in that remaining space, you'd only be able to fit 75 movies. That's still a lot of movies. Okay, most laptops today have 2 terabyte drives, and most of them have more than 15% free space. So, you know, you're not going to hit that limit very easily. Okay, now the next two are, I think, the problems that most people have problems with, and that is rate problems. Okay, and there's 2 types. There's the how long does it take something to happen, and how many can happen in a given amount of time. Okay, and so if you have a how long problem, you say, well, how do I do that? How do I do a how long? It's how much, it's the size that you want to upload or download. Okay, so remember, we're transmitting some information over the internet. Okay, divided by the rate. All right, like that. Now let's read the question and see, you know, how this works out. Okay, so how long would it take to upload 12 songs? Each song is about 5 minutes each. Okay, so you have 12 songs, 5 minutes each, over a 10 megabit per second line. Okay, so what's the size and what's the rate? Okay, so first of all, it's a how long problem. How long does it take for something to happen? So for how long, you do size divided by rate, like that. Okay, so now the size is how much you want to actually upload, and so that's going to be 12 songs. Each song is 5 minutes. Okay, and each minute is what? 1 megabyte in size. Okay, remember that? So well, let's do it one step at a time. Let's just do this. Okay, so we got 12 songs and they're 5 minutes each. 12 times 5 is 60 minutes. Okay, So it's 60 minutes worth of songs, not 60 minutes to actually upload it, but just 60 minutes worth of music. Okay, if you played all 12 songs one after another. Now, if you go back up here to audio, audio is the easiest one to remember because 1 minute is 1 megabyte. Okay, and so over here, if it's 60 minutes, well, 60 minutes is going to equal 60 megabytes. Okay, that should be pretty easy because again, every minute is 1 megabyte of information. All right, great. So that gives us the size. All right, so we got this part. But what about the rate? The rate, before I substitute in there, let's analyze it because I said here in the problem, it's 10 megabits per second. Okay, when I say a 10 megabit per second line, I mean like, the internet connection to your house can only sustain 10 megabits per second. Well, it's not that it can sustain that, but that's what the company limits it as. Okay, it limits it as 10 megabits per second. Okay, so so that's the rate, 10 megabits per second. Okay, but we should write that as 10 megabits divided by seconds, like that. Okay, this part here, megabits, is this part, and the per second is this part here. They put a P there, like miles per hour, they write mph, okay, but that's really, the per is just like a division, okay, and we want the units as a fraction because that's going to be important for working how the problem works. There's only one other thing we have to worry about, and that is that 1 byte, because you see this is in bytes there, like that, okay, 1 byte is equal to, if you remember, 8 bits. Okay, and that's again from the encoding. And you might say, well, why did they make our life complicated? Like if you take a USB drive, everything's in bytes. If you measure like the size of your files on your hard drive, it's in bytes. Everything, all these measures are in bytes. But when it comes to the internet, everything's done in bits. Okay, and there is an engineering reason, but there might be a marketing reason too. It makes the number look bigger, okay, because it's 8 times bigger than if you expressed it in bytes. But as far as our purposes are concerned, when you go to like Spectrum or Verizon or any of these places that are selling you internet packages, they always put it in megabits per second. So we're going to just work with that because, you want to be able to compare these packages. You want to understand what's going on. And so we have to do it the way, the people are doing it right now. Okay, maybe in the future they'll change, but right now everything is expressed in megabits per second. Okay, so now what? Well, now that we have all that information, we can go back to this and we can plug in. Okay, you say for the size, what's the size? Well, we determined that, for those 12 songs, okay, it's going to be they're going to be out 60 megabytes of information. Okay, so for the size here, we're going to place that with 60 megabytes. Okay, like that. And then for the rate, and we better put brackets around this because we're going to have a fraction of a fraction. It's going to be this, okay? And the reason it's a fraction of a fraction is because, you have this fraction here between, the numerator and denominator, but the denominator itself is a fraction in terms of its units. And so when you divide by a fraction, if you remember this, if you do A divided by B divided by C like that, you see that the denominator here is a fraction. What you do is you simply convert that into multiplying by the reciprocal, like that. So you can see that I was dividing by B divided by C, but that's the same as the multiplying by C divided by B. Okay, and so we're going to make use of that right now. Okay, so how? Well, let's take a look here. The meg here and the meg there, they actually cancel. Okay. Well, you know what? Let me do the fraction first. Okay, let's try to make this as easy for you as possible. First things first, let's isolate the numbers. Okay, so here we have a 60 and here we have a 10. So we have 60 in the numerator divided by 10 in the denominator, and that takes care of the numbers. Okay, so those numbers there are there. The units are the hard part. Okay, so you got megabytes here. Okay, like that, and divided by megabits divided by seconds, like that. Okay. So if this is too easy for you, I apologize, but I want to make sure that like I get every single detail in there. Well, 60 divided by 10, that's easy. It's 6. Okay, and then here we've got a fraction divided by a fraction, or a fraction with a fraction in it. And so megabytes here, but then we're going to multiply, rather than dividing by megabits per second, we're going to multiply by seconds divided by megabits, like that. Okay, so that's this little trick right there. Okay, that trick of dividing by a fraction is like multiplying by its reciprocal. We just did that, and going from here to there, that's what happened. Okay, now the next thing is we got to get the units cleaned up. So we have this part, and we have the mega in the numerator here, and we have mega in the denominator. And meg, that m, just means a million. You could just think of it as a million. You could think of k as 1,000, m as a million, G is a billion, T is a trillion, and P is, I don't even know what that's called past a billion, but you know what I mean. Like, it's just 3 more zeros. So if you got a million divided by a million, they just cancel out. So this goes away, that goes away, like that. And so now we have, and let me group together the bytes divided by the bits, like that, and then we have the seconds. Okay, so the seconds are in the denominator, and they're just sitting there. And then we have a byte divided by a bit. Okay, and there we go. And then you say, well, now what? And that's where we make use of this one right there. You could say, look, a byte is just 8 bits. So I'm going to take out that b, and I'm going to put 8 little b, take out the capital B, and put in 8 little b's there. Okay, all right. So right here, I have this, and I'm going to take out that capital B, and I'm going to put in 8 bits like that. Okay, and you say, what did I do? That byte is the same as 8 bits. So that byte is the same as 8 bits. And now you can see that you have bits in the numerator, bits in the denominator, and they cancel out. And so you just get on the next line. Again, I apologize for anyone that finds this, pedantic or too much details, but I want to make sure everyone, gets how this works. We have 6 multiplied by now 8. Okay, and the bits cancel the bits, and we have seconds, like that. And so how long is going to be 48 seconds. And there's your answer. Okay, under a minute. So yeah, it's 60 minutes of music, 60 minutes of music for us to listen to. Okay, but over this line, this 10 megabit per second line, it only takes like 48 seconds for it to upload. Okay, so this line is much faster in terms of transmitting audio information than our human ears are capable of hearing it. Okay, you wouldn't enjoy listening to the music at this speed because it would just sound like a blur to your brain. Okay, so I've done quite a few problems. Let me look at the chat here, see if anyone is has any questions. There's no one in the chat right now, so that's okay. I'll give you the opportunity, but if you want to watch it later, that's fine. That's the whole point of this. Okay, so did we answer the question? How long would it take to upload 12 songs, each song about 5 minutes, over a 10 megabit per second line? Yes, we did. It's 48 seconds, and there's your answer. Okay, so now what? Well, the other type of problem is the how many. Okay, so how many? You say, well, how does that one work? Okay, so the way this works is I say to you, look, how many of something are you going to be able to upload or download in a minute? All right, so I give you a time interval, I give you a rate. Okay, I give you a time interval, I give you a rate, and I ask you how many such files could you upload or download. Okay, now there's a few ways to do this, and I don't know if I want to show you the other way because I don't want to cause confusion for people that might see it two ways and say they don't know. Let me do it the way I did it in class, but another way is you could just multiply the time times the rate, and that tells you the amount of information you upload. Okay, and if you have the size that's uploaded and you divide it by the size of one file, that'll also answer the question. But the way I did it in class was kind of an analogy with this technique here. So instead of how long, okay, instead of a how long question, if you say how many, then it's the reciprocal. So it's the reciprocal of this. In other words, it's rate on top divided by size on the bottom, like that. Okay, so that's how you do a how many problem. Okay, so the rate is going to be, for this one, I better show you here, it's a 50 megabit per second line. Okay, so 50 megabits per second, so we'll write that as 50 megabits per second. Okay, notice again I changed the per to a division because that's what it means, divided by, so this divided by right here is that one, the size. And you say, well, what's the size? So this is a web quality image. Okay, so if you go back up to our chart all the way up here, a web quality image, which is low quality, it's synonymous for low quality. Images on the internet are low quality. Okay, the images that you take with your phone or like with an SLR camera, those are much higher quality. Okay, but image on the internet roughly about 100 kilobytes. So down here, when it comes to size, we're going to put 100 kilobytes like that. Okay. Well, now what? Well, now we have to, fix the units up, okay? And you'll notice that there's a few things out of sync here. There's meg on the top and kilo on the bottom, and there's bits here and bytes there, okay? And so now what do? Well, all right. So first thing I would do is I would isolate the numbers, get them out of the way and just like kind of isolate the numbers and then of course isolate the units. All right. So over here, how many is going to equal 50 divided by 100. Okay, so those are the numbers, and then we have the units here. For the units, what I'm going to do is I'm going to put the meg and the kilo together. So here's the meg and the kilo. Okay, now we didn't do that for the previous problems, but it makes sense to do it here. Okay, to actually separate the metric prefix from the bits and bytes. Okay, and that makes sense because it's just like saying a million. Okay, so if I say I have a mega egg, it's a silly word, but like that's a million eggs. If I had a million eggs, I could say I have 1 mega egg. Okay, or if I have 1,000 eggs, that's like 1 kilo egg. Okay, so whatever, the kilo part is just 1,000. Okay, so we'll put the million and the 1,000 together like that, and then we'll put the bits and the bytes together. So there's bits in the numerator, byte in the denominator. So we have little b divided by capital B like that, and then the per second here. It's its own unit off to the side here. So I'll put it over here. Okay. In other words, it doesn't cancel against anything. Okay. And you say, well, now what do I do? All right. So now you can start to simplify this. 50 divided by 100, that's pretty easy. That's a half. Okay. So there's our number. That's the numerical part of the problem. Okay. And now you say, there's a few ways to do this. You could go back up to the chart and you can say a meg. You can replace a meg with 1,000 Ks. But you know what? I'm going to do this as intuitively as I can. Okay, M is a million, so let me put a million there. 1, 2, 3, 4, 5, 6. And K is 1,000, so let me put 1,000 there. 1, 2, 3. Okay, like that. Okay, and you say, well, what's a million divided by 1,000? A million divided by 1,000 is 1,000. All right, so there you go. And then like if I were just doing this, I would just know that in my head, and I would just write down 1,000. And if you know that, go right ahead and do that, right? And then the little b divided by capital B, we have to go back up to this. A byte is 8 bits, and so over here, we'll leave the bit alone, and I'll replace the capital B on the bottom here, right there. I'm going to replace it with 8 little b's like that. Okay, so whoops. So this bit here was the bit there in the numerator. That byte there became 8 bits in the denominator. And then we still have that per second piece, okay? So there we go. There's the per second piece, okay? And now what? Well, now we can simplify a little bit further. Okay, so we have still 0.5, and then we have a million divided by 1,000, which is equal to 1,000. Okay, and we have a bit divided by a bit there, so that's just 1/8. Okay, right here. This piece here just reduces, the little b's cancel out, the bits cancel out, so by the 8, and then we have per second. Okay, and then you can take this and do this on your calculator, because now we can simplify that number. And I get this number right here. Okay, so how many is equal to that many per second? We still haven't quite answered the question, but we're definitely closer. What this says is 62.5 per second. Okay, I'll write it in English. You can download 62.5 images every second over a 50 megabit per second line. Okay, so that's a lot. Okay, like 1 second All right, not a minute, but just 1 second, you can download over 60 images. Okay, so 50, that gives you an idea how fast 50 megabits per second is. And remember, web pages are mostly images. Most web pages like 10, 20 images. And so that's why nowadays, modern lines, web pages download like that. Now, like if you lived in the ancient days, of the early internet, you click on a web page and you'd sit there waiting for it to appear. And I don't know how people had the patience to do that. But now you see, you click on it and it appears almost instantly because you're able to download 60 images. Now, we didn't quite answer the question because I didn't say how many in a second. I said how many in a minute. And you say, well, how do I go from a second to a minute? And the answer is just multiply by what converts it. Okay, so here we have seconds in the denominator, and remember, just multiply by one of those conversion fractions. So what do those conversion fractions look like? Okay, well, you want to go from seconds to minutes, so we're going to have seconds and minutes in this fraction. It isn't complete yet, so I'll build it up a piece at a time. Okay, and so here's the fraction, and the seconds are in the denominator, so we'll put seconds in the numerator here like that, and we want to go to minutes here like this. Okay, all right, and so we'll put minutes in the denominator. Okay, and then we say, well, we have to make this equal 1. We got the units in there, but it isn't equal 1 yet. So 1 minute is 60 seconds. Now it's equal to 1, right? Because 1 minute is 60 seconds. Okay, so that fraction's equal to 1 because the numerator and the denominator are equal to one another. 60 seconds is equal to a minute. Okay, so we didn't change the value of the number. Okay, and now if you multiply this out, look at what happens. The seconds here will cancel the seconds there. Okay, and you'll get 62 multiplied by 60, so there's your number, and then you'll have the seconds canceling out and you'll have per minute. Okay, so that might look funny to you, like that fraction there, but you could just read it out loud as per minute. Okay, and now what's that going to equal? Well, let me do that for you. Just multiply that by 60. It's going to be how many is equal to 3,750 per minute. Okay, and I even wrote the per there just to show you that means exactly the same as that. Okay, so let's go back here and see, did we answer the question? How many web quality images can you download in 1 minute over a 50 megabit per second line? And we came up with the answer that we can download 3,750 images per minute. Okay, so there's your answer. All right, these last two, the rate questions, I agree, I understand they are more difficult. It really is worth mastering them, not just for this test. I don't have time, but like I could go into other disciplines and show how the exact same types of problems, or not exactly, but the equivalent problems come up in biology, in medicine, and all that sort of thing. So don't think that you're wasting your time mastering these things just in computers. Okay, certainly useful here, but it's useful in many other places. Okay, and you can imagine, at what rate does your car consume gas? Okay, how many miles per gallon do you get? As soon as you hear the word per, it's a rate problem, and then you're into the situation where you have the two types of rate problems. Okay, all right. Anyhow, hopefully I've convinced you. Okay, that I'm teaching you something useful. Okay, all right. Now, the rest of this is not going to be problem solving because it's information. Okay, and I'm going to try to go a little faster than I did in my lectures because I want you to get a better overview. So I'm not going to go through all of the details, but hopefully this will be enough details to help you to understand why this is important information for orienting yourself in the computer world. Okay, so the next topic we studied were operating systems. Okay, so to understand operating systems, the first thing you have to understand is computers come with a distinction between hardware and software. That's not true of other machines. I know there are computers in cars, but like older cars are just the car function of a car. Okay, that's just a machine. It's got no software. Okay, or you're the software. You turn the wheel whenever you want the car to do whatever it does. Okay, so the hardware is the the physical component of the machine. Okay, and so that's what we mean by this word hardware. And another way to think of hardware is it's not just a physical component that you can touch, it's also the hard wiring. So, that CPU, which is this chip, and I showed you a picture of it, there's billions of little transistors in there, and they're all hardwired. You can't go into that chip, open it up. Oh, you break it if you did, but if you open it up and then rewire it in order to give your computer different functionality, that's not how we give computers different functionality. Okay, so hard can also mean hardwired. All right, that you can't change the way the wiring is to give the computer a different functionality. Okay, and yet we know that that happens because your phone, when you first get it, it probably doesn't have clouds and sheep. Okay, so we're going to pick on clouds and sheep as our app. Your phone doesn't know how to play clouds and sheep. But you know what? You can go to the Google Play Store, download it, and now your phone knows how to do that. Okay, so that's what this other part, the software. The software is how you can teach your phone to do more things. Okay, and so software are the instructions that you give the computer to change to do to give it new functionality and new features. Okay, and you can add software and you can remove software, and it's just as easy as a click of a button. So software, another way to think about it is that it's soft, it's easy to change. Okay, hardware is hard to change, software is easy to change. Okay, so those are the kinds of metaphors that came up in people's mind when they came up with those words back in the day. Okay, so more properly speaking, software is the instructions that you give your computer, and they're programs. Those are the programs or apps. Okay, and by the way, when I say computer, I know this is like computer technology, but it's everything now. Like, what isn't a computer today? Your phone is a computer, your tablet is a computer, your refrigerator is a computer, your car has a computer in it, your smart TV has a computer. So everything has a computer. So everything has both hardware and software in it. Okay. All right, great. Okay, now I gave you some examples of hardware components in a computer, just so you know roughly what's in there. But we not an engineering course, so there's the CPU, and that's the brains. That's where like all that CPU, that adding machine that I designed lives inside the CPU. Okay, memory is it's also known as RAM. This is the memory that's used as a computer runs. The more RAM you have, the more programs you can run at the same time. Okay, storage is where your apps and the operating system are stored, where your files are stored. Okay, so the difference between memory and storage is that when you shut off the computer, anything that's in memory disappears. Okay, so the memory is only temporary memory while the computer is running. The storage is where all your files are stored. Okay, so when you shut off your laptop, like a lot of you will just close your laptop and it goes to sleep, but you can actually shut it down and turn off the power completely. Or on a desktop, you just shut it down and unplug it from the wall. It's not running at all. Well, whatever's in memory is gone. Okay, so it's just that memory is just the temporary memory that's used while the computer is running. The storage is where all the files are stored, so that when you turn on the computer again, your pictures are still there. Otherwise, I don't know, it would be kind of useless. Computers would be kind of useless other than that. Now, there's the graphics card, which is like, the thing that draws to your screen. And that's not too interesting. It's hard to change the graphics card anyhow. But, for people that are into gaming, you want good graphics cards. So it's good to know about that. And then everything is plugged together by this thing called a motherboard, sometimes abbreviated as MOBO motherboard. Okay. And then finally, there's, the peripherals. And you say, well, what are peripherals? They're literally like everything else. Okay. Like all the stuff that's kind of external to the computer. Okay, that's what the word peripheral means. Okay, like your mouse, your keyboard, the monitor, and so on. Okay, the monitor, I know that's where the pictures are drawn, but the circuitry, the actual electronic circuitry that does the drawing, is inside the computer itself, and that's the graphics card. So the graphics card does the calculations of what to draw, and then it sends that drawing to the monitor, and the monitor then just renders it on the screen. Okay, there it is. All right. Okay, so a little bit about the hardware. Okay, software. So software is actually broken into two layers. Okay, and now we're getting into the meat of what this lecture or this section was all about. Okay, so it's broken into two layers. It's broken into the applications or programs. Okay, so if you're on your phone, you tend to call them apps, and if you're on a computer, you tend to call them a desktop, you tend to call them a program. But they're really the same thing. They're the same things. Okay, so the apps are like what you interact with. You have an app, clouds and sheep. Of course, you want to say, I'm going to waste some time playing clouds and sheep. You press on it, and up comes that app. Okay, and then you interact with it, you play with it, and so on. Okay, but there's something running behind the scene that's making everything work properly. It's orchestrating everything. That's the operating system. It's also software, okay, because it can be changed. Okay, it's hard. It might be hard for you to change the operating system, but it's not hard to change it. I mean, if you know what you're doing, you can actually change the operating system pretty quickly. In fact, when you up, when like Androids, or I guess iPhone, I don't have an iPhone, so I don't know for sure how they work, but with an Android, when they update, they say there's an update, and then it just spends all this time doing all this stuff, and then it reboots and it comes back up. And you know what it did? It actually changed the operating system. So the operating system can be changed. It's just not something that you usually do. Okay, um, an expert does it, or it's done behind the scenes by the system itself. Okay, the old operating system installs the new operating system. Okay, so I think I kind of said this already. The apps are what you interact with. Okay, I don't know, calculator program, yeah, a calendar program, Microsoft Word, all those things. Okay, those are things that you as the user use directly, and those are called applications or programs. And the operating system, what it's really responsible for is making the hardware run properly. Okay, so that's really like, there's a kind of a specialization. The operating system is specialized in making the hardware run properly. Okay, now you say, well, don't the apps need the hardware? Yes, if the apps need the hardware, they have to ask the operating system to do it. They got to go through the operating system to the hardware. Okay, and that's the way computers have been designed. So like when you ask someone, what kind of phone do you have, they could say, well, this is a Samsung, like my phone here is a Samsung. That's who manufactured the hardware. But the answer that most people expect is that it's an Android. Okay, they'll say, well, you're running Android. They'll tell you the version of Android that you're running. Okay, and that's kind of important because the operating system really sets the entire environment in which everything is going to be happening. Okay, and the reason is that the applications have to be able to talk to the operating system and back and forth. Okay, if the apps can't talk to the operating system, then those apps don't run on that phone. That's it, period. Okay, so examples of apps. Well, I already gave you my clouds and sheep. I'm picking on that game right now, but there's lots of games. Okay, calendar, like the calendar program, Microsoft Word, I just gave an example. Those are all apps. Okay, examples of operating systems are like Android on the phone, iOS on the phone. Okay, Windows 10 on a desktop or laptop, Mac OS X on a on Apple products. Okay, Ubuntu Linux, which will run on a lot of things too, including Macs. Okay, and Gentoo Linux. I didn't show you Gentoo Linux, but I'm actually a Gentoo developer. If you go online and you Google my name, you'll see that I'm associated with Gentoo Linux because I work on operating systems as part of my research. Okay, so like when someone says, well, what are you running, or what's your phone? You say an Android phone. You're really talking about the operating system, and that's again because what you're really saying is that the Android operating system, that's the environment in which I'm working, and all of my apps are Android apps. Okay, and so on. Okay, if you're on the iPhone, then all of your apps on that phone are going to be of a different family. They got to be apps that run on the iOS. Okay, so this splits our world. Okay, splits the world of computers up. Okay, now why was it designed this way? Because the disadvantage, I guess I talked about the disadvantage already. The disadvantage is that if one app runs on one operating system, it may not run on another. The classic example I give here is Microsoft Access. So Microsoft Access, which is a databasing program, and we're going to talk about databasing after the test. Databasing programs only run, Microsoft Access only runs in Windows 10. Okay, it does not run on a Mac. Okay, so there's a disadvantage to having broken up your world into different operating systems. The advantage, though, of creating operating systems is that it makes your computers run fast. Okay, that's one of the things that operating systems are supposed to do. They specialize. They specialize in running that hardware, and they've gotten good over the years. So they run the information fast. They make sure it's secure. Your information's secure, so that no one can get at it. Operating systems are what are responsible for encryption. Robustly means that they make sure that things don't crash, because it's very easy if you've got a bad operating system to crash things. Okay, that means your phone locks up. You can't do anything with it except turn it off. Okay, sometimes even that doesn't work. You have to pull the battery, like in the older phones. Okay, so those lockups can be pretty bad. And the other thing it does is this one's not so much for you, but it's more for developers. It basically frees the apps so that they don't have to worry about the hardware. Okay, otherwise the apps themselves would have to worry about the details of the hardware. Okay, and that would make life really ugly, because every app would then have to know about every type of piece of hardware out there. Okay, so yeah, there was an advantage to splitting this up, but the disadvantage was that now you've kind of fragmented the the operating system world into a bunch of different families. Okay, so people will swear by their iPhones, or they'll swear by Android, and what's going on there is because they're it's not so much the operating system, but they're familiar with the Mac apps, okay, from the Apple Store, or they're familiar with the Android apps that from the Google Store, okay. And so, and you say, but I really like that Mac app. Nah, I've got an Android and can't run it. Okay, so that's what happened. It basically led to incompatibility, but there's ways around that incompatibility, okay, and and these things are growing up. Okay, I'm going to give you an old solution, which I probably should drop this in the future, but because it's going out of style. Okay, but it's this idea of dual boot, and what dual boot means is you literally turn your computer into two computers by partitioning the hard drive, not physically splitting it, but it acts like two hard drives. Okay, and on one hard drive you install Windows, on the other hard drive you install Mac OS X, and then when you go to boot the computer, you could say, boot it into Windows this time, and then your computer looks like a Windows computer. Okay, and then you reboot it, and then the next time it comes up in Mac. You say, I want Mac this time, and it comes up in Mac. So you literally can have both Mac and Windows on the computer. They can't both run at the same time. You can never have two operating systems running natively on the same computer. Okay, it's either going to be Windows running natively or Mac OS X running natively, and I'll tell you what natively means a little bit better in just a minute. Okay, so it's one or the other, but not both. Okay, it's exclusive or logic. Okay, so one or the other, but not both. All right, and also, like whatever you did in the Mac side, all those files in the Mac side, they're not available on the Windows side, and all the stuff that you did in the Windows side is not available on the Mac side. So it's kind of going out of style, because this kind of like split brain, gets kind of annoying. You're working in Windows and you can go, I need that thing from Mac, and you reboot. Okay, so on. Well, the better way is, and this is becoming increasingly popular, and probably in the future you may be doing this and not even know you're doing it, because it'll become seamless as part of the operating system. The operating system itself might be able to emulate other operating systems. This is virtualization, and in virtualization, what happens is you have a program, and this program actually emulates an entire computer. Okay, so what's that? Sorry about that. I tried to mute in time, but I didn't get to it. Okay, virtualization is it's like an app. It's a program, but this program actually emulates an entire computer. So you can actually run a computer within a computer. Okay, now I can tell you the difference between a native operating system and a virtualized operating system. Okay, so when you first boot your computer, when you first turn on your computer, it has to find an operating system, otherwise it can't run. That first operating system that starts up when your computer starts, and it runs directly on the hardware. There's no layer between that and the hardware, between that operating system and the hardware. That's called the native operating system. That's the operating system that's running natively on the hardware. Later, as you're using your computer, you could start up this, like VirtualBox, an emulating program, and then you have an emulated computer within your computer, and you can start up an operating system within that. That's a virtualized environment. That's a virtual operating system. Okay, now you can have one and only one native operating system, because it loads when you boot the computer, and it only disappears once you shut the computer off. As long as your computer is running, that operating system is operative in the background. It's running in the background. Okay, but for a virtual machine, you can open one up. You can open up a second one. You can open up a third one. Okay, you can literally have like as many computers, emulated computers, virtual computers inside running on your computer as you have RAM, as you have memory. Okay, so you say, why would I want more memory? You might want more memory if you're going to run a lot of computers within computers. Okay, and if you do that, then yeah, you need to actually need more RAM. Okay, but if you have lots of RAM, if you have lots of memory, you could open up you could have like a Windows computer, and within that Windows computer you can emulate Mac, and then you can also emulate Linux, and so you can have natively running Mac. So it's natively running Mac, and it could be virtually running Windows and another one virtually running Linux. And so you can have multiple virtualized operating systems, one and only one native operating system. Okay, you can never have more than one native operating system running at the same time. I don't even know, understanding how these things work, I don't even know how you would do that. It doesn't make any sense at all. You can have many apps running at the same time, and so you can have as many emulated computers as you like, but you can only have one running operating system natively. Okay, So I think I made that point right here. Okay, so uh, that's why I actually demonstrated emulators for you, because it's kind of hard to get your head around. But one of them was VirtualBox. Okay, and I showed you the installation of Ubuntu Linux within VirtualBox. I also showed you BlueStack, and well, first I should say that VirtualBox is good because you can have any operating system running on any other operating system. So any operating system natively, any operating system virtualized. Okay, BlueStack is specialized for emulating Android on Windows. It actually works on the Mac too. I didn't know that when I did the video, but yeah, BlueStacks. There's BlueStacks for Windows and BlueStacks for Mac, and if you start it up, it actually emulates an Android environment. So you can have Android on your laptop, okay, so that you can play Clouds and Sheep, of course, okay, or whatever app you need, okay, and it could do a lot more things than I showed you, okay. I just kind of like gave you a little flavor into what's going on, but there's others too, and I didn't tell you about these. There's crossover for the Mac, okay. It costs money, but it allows you to run Windows programs on a Mac. Okay, so that's how you could do Microsoft Access on your Mac. Okay, and you say, well, there's a whole zoo of these. Okay, yeah, you know what? If you really are interested in this, you just Google for emulators Mac on Windows. Okay, enough about that. All right, so there's a little story about operating systems and how they multiple operating systems can relate to one another and so on. Okay, one of the most important things that operating systems do for you is they do encryption. And so what is encryption? So encryption is this idea of scrambling the data on your storage device. Okay, so storage devices, that's where you store your files. It could be the hard drive inside your computer or a USB stick. Okay, so you want to scramble this information on the USB stick so that it cannot be read or used or descrambled without a password. Okay, and you say, well, why would I want to do that? Well, people lose USB sticks all the time. Okay, go into the computer lab and they're left behind all the time. Well, imagine you've left behind some important information like your social security number, something crazy like that. Well, that's terrible, because someone will get that, and if they're good, they'll turn it in or try to find the owner. But you can't depend on the good nature of humans. Someone will keep. There's probably someone out there that'll keep it and try to use it. And so to prevent your information from being lost, or not being lost, but falling into the wrong hands, you can encrypt. Okay, so again, it's a encryption. There's a mathematical algorithm which scrambles the information, and you look at the information when it's scrambled and it doesn't make any sense to you or to another computer. And if you want to descramble it so it's useful, so you can read it or another computer can use it, you need a password, a secret password that you carry around in your brain. Okay, there you go. All right, so that's what encryption is, okay? And the modern encryption is so powerful that you have the password. When you first set up the encryption, it also gives you this recovery key, okay? And the recovery key is important. You want to store that somewhere in case you forget the password, because you can get in with the password, you can get in with the recovery key. But if you lose both the password and the recovery key, you will not be able to get at your information, okay? In theory, it's possible, but practically it's so difficult that you wouldn't want to spend the money, and I don't even know if there's any amount of money in the world that could do it. Okay, so yeah, this encryption is that powerful. Okay, so that's why I put here, with great power comes great responsibility. Okay, so just be aware of this. If you're really going to encrypt these devices, be aware that you have to have a properly memorized password so that you're not going to forget that password, and make sure not to just skip that step and throw away the recovery key. Keep that recovery key just in case. Okay, all right. When you get used to this, hopefully you'll try this. Okay, try it on something that's not critical, because it's not that hard to use BitLocker on Windows. If you try this, try it with something which is not critical. But once you get used to it, you go, you know what, I see how this works. I'm not going to make a mistake. And then you can start to use it in your day-to-day life. Okay. So by the way, some companies demand that you use this. Okay. Companies that carry sensitive information. Okay. So, all right, so there's this other thing called formatting a drive. Encrypting is one thing, there's formatting. Now, formatting it's not really related directly to encryption, but the same programs that do encryption also do formatting, so you need to know about it so you don't make a mistake, okay? And formatting just means wiping out the device. Okay, so you have a USB drive and it's got a whole bunch of files on there, and you go, well, you know what? I don't want to throw every one of them to the trash. I'm just going to wipe it clean in one shot. That's formatting. Okay, sometimes you want to do it, sometimes you don't. But when you go to encrypt, make sure you keep the two separate, because both on Mac and in Windows, the buttons are very close to one another. Okay, so just keep that in mind. So that's the difference. Encryption is this scrambling so that you can't descramble without a password, and formatting is wiping it clean so that the device is pristine like it was when you first purchased it. Okay, now last thing before we move on is, how do you choose a good password? Okay, so there's like this way we used to do it was like mix upper lowercase letters. No, that's a terrible way, because it's easy for computers to guess it and hard for you to remember. The opposite, hard for computers to guess but easy for you to remember, is to simply memorize 6 words. Okay, they must be unrelated. Okay, don't do 6 words which are a sentence. All right, I know a sentence is easier to remember than 6 unrelated words, but if it's a sentence and the words are related, a computer will figure it out. If they're unrelated, the computer is in a lot worse situation because it doesn't know how to relate the words. Okay, so basically this is called a passphrase. It really is a password, but we call it a passphrase because it's more than one word. So 6 or more totally unrelated words, and you're good. Okay, that's the way to choose your passwords. All right. By the way, most password systems will even allow with space in there, so you don't have to put the words up against one another. Okay, there you go. That's it for operating systems. The next thing is the internet. Okay, so before I jump in there, let me just take a quick sip of my coffee. I need a little bit of energy here, and I'll mute so that you don't have to hear me. All right, let me see if there's any questions in the chat. Nope. No one's in the chat. Okay, so I'm talking to empty air. Hopefully you're watching this later. All right, so the next topic was the internet. Okay, now with the internet, the topics that I chose, it's obviously all of these things are huge topics. In an engineering course like operating systems could be like 2 courses. Okay, networking can be 1 or 2 courses as well. Okay, so there's a lot of information through the internet. So, and an operating system. So you say, what should I teach you? And I gave you a bit of technical information, but enough information to really cover 2 things with the internet. One is security. Okay, because you don't know where your information is going on the internet. Okay, well, you didn't before this, but now you got a better idea of where that information is going. Okay, and like who can see it and who can't, and and how can you mitigate against people eavesdropping on your conversation with your bank. Okay, and there are ways of doing that. Okay, and they're built into the internet already. But if you don't know about them and things go wrong, you want to be informed. You want to be informed. Okay, so that's one thing. The other thing is I gave you a little bit of a flavor of the new types of technologies that the internet has made possible, like like bitcoins. That's a whole new type of currency. It's cryptocurrency and fiat currency. They're 2 totally different types of currency, well, they're currency, so I shouldn't say totally different. You can both use US dollars and you can use bitcoins to buy and sell things. Okay, but it's a little bit different. It's a bit more than that. Okay, it has to do with who controls the money supply. Okay, anyhow, all right, so that's what that's what these topics are going to be about. Okay, so how do we understand this thing, the internet? Like, it's everywhere, isn't it? Okay, all right. So to understand like where this internet is and what it is, first you have to understand what a local area network is. It's usually abbreviated by the name LAN. It stands for local area network. You say, what is that? What's this local area network? It's basically like, just an area, like maybe your house, or like a building at the college or something like that. And there the computers are wired, but they don't talk to one another through the internet. They talk to one another directly. Okay, I don't want to get into what directly exactly means, but they talk to one another in a more intimate way than computers on the internet do. Okay, so this is known as a local area network. Okay, and so like in your home, you could have like your phone hooked up to your wireless router. You could have your laptop hooked up to your wireless router. You might have a desktop and it's hooked up to your router via wire. Okay, all these things. Well, all of those devices, if they have to communicate with one another, which they sometimes do, they'll do it directly. They don't go through the router. So that's the second thing. What's this router thing? The router, it's usually set up by your ISP. I didn't put ISP down here, but that's your internet service provider, like Verizon or Spectrum or whoever. Okay. When they bring the internet to your house, they give you this thing called a router. They also give you a modem, but the modem part is just like the conversion between cable and Ethernet. The more important part is the router part. The router part is what takes the information on the local area network and sends it out to the internet. So really what a router is it's a device that connects one local area network to another local area network. Okay. And so you could think of the entire internet as this patchwork of local area networks that have been glued together by these routers. Okay. I don't know if I can think of an analogy. Maybe like the mail system, like every house is its own local area network. But how do you send a letter from one house to another house? Well, you give it to your mail person, okay, and they carry it for you, okay. So the mail people are like the routers, all right. So give you a bit of an analogy there, okay. So once again, the internet is a bunch of a patchwork of local area networks glued together by routers. Okay, so what's this information that they're passing between them? Well, the information is organized, and it's organized into these things called packets. And packets are like little bundles of information for transmission on the internet. Okay, and you can think of them as like the letters, snail mail letters. All right, so I think this analogy kind of works, and it's probably what was in the back of people's minds when they designed the internet. And so, these packets, that's where all your information is, and that's what people can see, that are running these routers. Like think of a mail person that gets one of your letters. They could see your address, they could see the address of where it's going to, and if they open it up, which they're not supposed to do, but if they did, they could see the contents. Okay, so what is a packet made out of? All right, it's made out of the source IP address. Okay, that's you. That's the source where the packet is coming from. It's also got the destination IP address. That's where it's going to, where that packet is going to. And of course, it's got the contents. It's like what information is being carried in the being piggybacked on this packet. Okay. So I said this word IP address. You go, well, what is this IP address? Okay, that's how computers are identified on the internet. It's basically a sequence of numbers which identifies computers on the internet. Okay, they're like like every house has a home address, and every computer has an IP address. Okay, at least one. They can have more than one, but they have at least one. Okay, now there's two families of IP addresses, and you should be able to recognize them because this is how you get identified in the internet. So it's kind of worth knowing what your IP address is. And if you want to know your IP address, you could just go to this website called, all one word, what'smyipaddress.com, and it'll tell you what your IP address is. Okay, and you say, well, how does this website know? Because you're announcing your IP address to the other sites. So you're announcing your not your full identity, not your name or whatever, but at least a little part of your identity is being disclosed by these packets. You say, well, I want to avoid that. Well, hang on, I'll show you how to avoid that in a minute with the Tor browser. But for now, the IP address is, how you get identified, or how your computers get identified on the internet. And there's two families. There's the IPv4. Okay, these are the older ones, but more popular. And they're 32 bits in size. Okay, so that's a sequence of 32 ones and zeros, which means that there are 4 billion different IP addresses, 4 billion different IP version 4 addresses. We've run out of them, meaning we've already allocated them all. We've already given them all away. Okay, we being a consortium called Aaron. Okay, that gave them away. Now, there's the newer ones, and they're becoming more popular because they have to. Okay, and these are IP version 6. These ones are 128 bits in size, so this is huge. Okay, and 128 bits in size. So these are actually 4 times the size of those in terms of ones and zeros. But if you work it out, that turns out to be 3.4 times 10 to the 38. Okay, and you say, well, what's this 10 to the 38? I mean, this is a decimal number with 38 digits in it. It's huge. Okay, unimaginably big. And the idea was, we're going to make this so big that we'll never run out of these again. Maybe right. Okay, now what do they look like? The IP version 4 look like this. They're just like 4 numbers separated by periods, and the IP version 6 look like this. Okay, and they are basically hexadecimal digits. Okay, so hexadecimal, just remember, that's like 16 unique digits. So it's the digits 0 to 9, and then A, B, C, D, E, F. Okay, and you can see there, you can see an F, an E, an 8, and 0. Okay, and so on. You'll never see like the letter M or anything like that, because F is as far as they go. Okay, anyhow, there you go. So there's the IP version 4 and the IP version 6. And just one more thing before we move on to other things about these addresses. The IP version 4, they give you a little bit more privacy than the IP version 6, because on the LAN, on one of these local area networks, they basically make use of what are known as private IP addresses. Now, these private IP addresses, they're local, okay, and they can be repeated between LANs. In other words, my LAN here could have an IP address 192.168.1.1, and another LAN, like in the neighborhood, but not connected to mine directly, but through the internet, another LAN somewhere else could also have the IP address 192.168.1.1. So they're repeatable, they're recyclable, okay, and they can't be used on the internet because they don't uniquely identify every computer. Because if the computer is not uniquely identified by the IP address, how can you route to it? Okay, how can you know where to send the packet? Because there'll be several computers with the same IP address, and the router will go, I don't know which one you want me to send it to. Okay, so there are these private IP addresses, and they're used on LANs. They share one and only one public IP address. That's the IP address on your router, the IP address that faces the internet. Okay, so many private IP addresses can share one public IP address. Why does that give you a little bit of security? Because if you're at the college, or a little bit of anonymity, because if you're at the college, okay, someone out on the internet doesn't know your particular computer and your particular identity. All they know is that the IP address belongs to the router for Duval College. Okay, so the best they could say is something like, someone at Duval College is doing this thing. Okay, whatever it is that you're doing that's exposing your IP address. Okay, they don't know who though, because there could be hundreds of people on that LAN, and they wouldn't know which one. So a little bit of privacy. With IP version 6, there's no such split between private and public because there's so many of them. There's no need to try to conserve them. The whole reason for the private-public split wasn't just for anonymity; it was to try to conserve. Okay, so there you go. Now, there are questions about how to get privacy into IP version 6. More than privacy, anonymity, and people are working on that. But there it is. Okay, so just so you know that IP version 4 has this private-public split, and because of the private the split, on a LAN you have a little bit of privacy. You can identify LANs by the public IP address. You can't identify individual devices inside of a LAN by the public IP address. Okay, enough of that. There's one other thing you need to know about, and that is DNS. You may not have even heard about IP addresses before this course. And you go, well, they're numbers. I've never seen these before, and yet you're using them all the time when you surf the internet. Yeah, that's because you work in terms of domain names, and those are like the website names, like www.google.com or www.dyc.edu. That's kind of the name you carry in your head. And since everything starts with www, mostly you just remember dyc.edu, okay? That's kind of easy to remember, isn't it? Okay? And you don't even have to remember that because like a lot of these are stored in your browser or in your history or whatever, okay? And so they autocomplete. But yeah, you know what I mean. Like the name, dyc.edu, that's easy to remember. Google. We don't even have to say google.com. We just know Google, okay? And there's Etsy. Etsy.com or Etsy, or Amazon, Amazon.com. It's easy to remember those names. It's hard to remember numbers because our brains don't work that way. And so, yeah, we remember dyc.edu, but the computer needs that number right there. It needs the IP address. And so you say, well, how does your phone know when I go to, when I check my email, Duval College email on my phone, I go to dyc.edu. And how does my phone know to go to that IP address? It has to, because that's the only way it can construct a packet. The packet doesn't contain the domain name. It contains the IP address. So it has to construct that packet. It's got to write the letter. Okay, and being a computer, it writes that letter very, very fast. Okay, so it's got to construct that packet. It's got to put that IP address in there, okay, as a destination IP address. How does it know that destination IP address? There is a service out on the internet. Okay, it's like a phone book, which will convert this name to that IP address there like that. Okay, it's called DNS or Domain Name Service. The service is provided by special computers called domain name servers. Okay, and they're out there, and then your phone, without you even knowing it, so this is happening silently behind the scenes, without you even knowing it, that your phone is doing this kind of communication with these DNS servers all the time. And your phone, without you even telling you, is sending those packets to those routers. Okay, so now we're in a position to understand what kind of information gets disclosed as you use the internet. If you have no other kind of mitigation, so don't get paranoid yet, okay? If there's nothing else going on, okay, if we're like in the internet of the old days before there was any encryption, or really before there was any kind of business being done on the internet, because business pushed people to encrypt, okay, to keep secrets. All right, you can't do business with your bank on the internet unless you can keep your bank account secret. There it is. Okay, so without any mitigation, these are the four things you can think of as being disclosed as you use the internet. Your source IP address, okay, that identifies you because it's your IP address. Again, maybe it just identifies the LAN in terms of IP version 4, but I wouldn't, a little bit of anonymity, not a lot. Okay. You disclosed your destination IP address. It's who you are and who you're talking to. So the source is who you are, and the destination is who you're talking to. So anyone that's running a router knows that you are talking to some destination. Okay, like if I'm banking, they know it's me, and they know I'm talking to my bank. Without any other mitigation, they can also see the contents. They can see what I'm saying to my bank. Okay, and these three here, because they're part of the route of the packets, and the packets pass through the routers. Okay, the routers, anyone that's running these routers, and there's about 10 of them between you and your bank, something like that, maybe 5 at best. Okay, but usually around 10. Anyone that's running those routers can see all of that information. Okay, that's where your information is getting disclosed. And finally, these other DNS servers, they will see your the domain names of the sites that you're visiting. Okay, effectively they know your browsing history. Okay, so you go, oh, this is terrible, I want to keep this all a secret. Well, that's kind of the point. Like, first I got to tell you what's disclosed, and now I'm going to show you how it's what you need to do to keep it a secret. Okay, so the first thing that you can do to keep it a secret is not even something that you need to do. Okay, so put it down here. You don't have to do anything. You just have to know that it's going on and make sure that it's working. So the only thing you have to do is, like, you just have to make sure that your browser isn't giving you this warning. Okay, if all you care about is hiding the contents, like up here. So, that's what most people do. Okay, you say, well, I don't care that people know that I'm talking to my bank. I don't care. I just don't want them to see what I'm saying. I don't want them to see how much money is in my account, okay, or things like that. So if my ISP, I have Spectrum here. If someone at Spectrum says, I'm going to watch this professor here, I'm going to watch this guy, and sees that I'm talking to my bank, I could go, yeah, all right, fine. Well, there's nothing wrong. I'm just talking to my bank. But I don't want them to see how much money is in my account. I don't want them to see my bank account. I don't want them to be able to see my password so they can get in later and that. So if that's all you care is to just hide the contents, the password is in the contents, then your browser's already set up to do that. Okay, and this is known as HTTPS. Whoops, let me scroll down a bit here. HTTPS, and it basically means encrypted web communication. The way it works is through this asymmetric key encryption. Okay, so asymmetric key encryption, what that is that in order to encrypt the information, you don't encrypt with just one key. Okay, the encryption that I just talked about a minute ago for the hard drive and all that, the same password that you use to encrypt is also used to decrypt. Okay, that's known as symmetric key, and that's fine for a hard drive. Okay, because that key is never leaving your brain. All right, but on the internet, you have to be able to transmit keys to the other side, because I got to give the other side a key in order to do the encryption. So the bank has got to give my browser, like Firefox, my bank has got to give Firefox a key to do the encryption. Well, if the same key is used for encrypting and decrypting, well, then whoever can intercept the encrypted communication can also intercept the key, and then they can just decrypt it. So this is like if you want a snail mail equivalent of that, it's like sending a package through the mail that's locked, and you tape the key to unlock it to the top of the box. That's silly. How's that going to work? You've got this box, it's locked, but the key to unlock it is right on top. So whoever can get the box can also get the key. So that's not the way it works on the internet. On the internet, there's another kind of mathematics. It's known as asymmetric key encryption. And there's a public key and a private key. The public key encrypts but cannot decrypt. Okay, so encrypt, think of it as locking. The public key can lock the lock, but it can't unlock the lock. That's a funny kind of a lock, isn't it? So the public key can lock it, but can't unlock it. The private key can unlock it, but not lock it. Okay, so my bank will send out the public key to whoever asks. Okay, and so sends my browser the public key. My browser encrypts with that public key and sends it out on the internet. Everyone has the encrypted packet. Everyone has the public key that encrypted that packet, but the public key cannot be used to decrypt it. Okay, the public key has already been used because it encrypted it, but it cannot be used to decrypt it. All right, or in terms of a lock, the public key was used to lock it, but the public key can't unlock it. So that's it. This packet is safe out on the internet because no one out on the internet can unlock it. Who can unlock it? Whoever has the private key, and that's only my bank. Okay, absolutely ingenious if you think about it. I don't know if you could build such a lock in the real world. Okay, like a lock with two different locking mechanisms, one with a private and public key, but mathematically you can. Okay, and so that's how the encryption on the internet works. Okay, and so there's the public key that you share with anyone and can only be used to encrypt, and then there's a private key that you share with no one, and that's can only be used to decrypt. Okay, and it's held by the server that sends out the public keys. Okay, like the bank. All right, so a little bit of a quick explanation for how private public key encryption works. And the only problem in this system is, what if someone sends out public keys that say they belong to my bank, but they really don't? So some hacker out there says, I'm going to pretend to be a bank. Okay, because there are programs to create these public keys. So I'm going to create a public key, and I'm going to pretend to be a bank. Look, it's illegal, but that doesn't always stop people. Okay, so for your browser to recognize if a key is authentic or not, in other words, not fake, all right, it looks for a signature on it. Okay, and that signature is generated by what's called a certificate authority. So when these public keys are made, they have to be signed by a certificate authority so you know they're not fake. Your browser can do encryption with a public key that is not signed. All right, let me say that again. Your browser can do encryption with a public key that is fake. It's not been signed or not been verified by a certificate authority. But it throws a warning at you. It's going to say something like, I'm going to do encryption here, but you realize that I can't tell you whether this is a real public key or a fake public key. Like on Twitter, you have those blue check marks to verify people, because anyone can pretend to be anyone on the internet, right? So on Twitter, it's the same with public keys as it is for Twitter handles or whatever, any social media. You just say, look, I'm Albert Einstein. Okay, like you could just choose a name, Albert Einstein, for Twitter. Okay, and what Twitter does is when they verify people, they'll give them a little blue check mark. Okay, I don't know how that process works, but that's really what the certificate authorities are doing. They're just putting little check marks on these public keys that your browser can check so to make sure they're not fake. Again, your browser can use fake public keys, but when it does, it warns you. Okay, so you say, well, why did I just hurt your brain with all of that information? So now you know how this symmetric key encryption works. You also know what your browser is going to tell you about these public keys that it gets, and now you can make sense of those messages. A lot of people get these messages, they can't make sense of them, and they don't know how to act on them. Okay, do public keys break? Well, yeah, they do. I mean, there are fake public keys all over the internet. Okay, and the other thing too is they expire after a certain amount of time. So yeah, you want to know about this. You want to know about this. You want to have a sense that when you're talking to Amazon, when you're doing any kind of business, Amazon, banking, whatever, you're doing this public-private key encryption back and forth, and something can go wrong. Your browser will tell you, and you'll know now what's going on. Okay, so a little bit technical, I agree, but hopefully you'll understand why I want you to have this going forward in life. Okay, all right. Another way that you get tracked on the internet. So now we're going to move from encryption to actually, which just secures the contents, to actually anonymity. And the difference is security is just securing the data. Anonymity is securing your identity. It's stronger. Okay, so there are these things called cookies. Okay, and it's a nice name for them. They sound, everyone loves cookies, but they're little pieces of code that are put inside your browser that identify you. Okay, now cookies can be good or bad. All right, when you log into a site, like you log into Dooville, right, you don't have to keep putting in your username password every time you browse Dooville's website. It knows that you've already logged in. You go, well, how does it know it's me? Okay, how does it know it's me? Remember, it doesn't have your private IP address, so there could be someone else on the same land that's also doing going to the Duval website, going into their email, Duval email, and so on. And how would the Duval server know one or the other? Well, this little cookie says I've already logged in. I've already logged in. So the server at the other end, the email server web page says, is it really you still? Show me that cookie. Show me that cookie. Let me see if it's still you. Okay, and your browser will say, here's the cookie. See, it's still me. I logged in a minute ago, and the other side goes, yeah. Okay, see, it's you. And so that's a good cookie, because that cookie says, you've logged in. And without those cookies, you wouldn't be able to stay logged in. Okay, you'd have to keep entering in your password. So cookies are good, but they can also be bad. And the way they're bad is if you're shopping for something, okay, and it doesn't have to just be shopping. It could be anything, but shopping is an easy example. And you're shopping for lawnmowers, because this is my favorite example, because it happened to me. And your browser gets a cookie, and this cookie says this person likes lawnmowers. Loves lawnmowers. Well, then other websites will say, can I see that cookie? Oh, you're that lawnmower loving person, aren't you? And then they throw these ads for lawnmowers. And for like weeks and months afterwards, you're going to get lawnmower ads, because they know you from that cookie that's inside your browser. And so that's kind of annoying. All right. Now, there are ways of clearing cookies out of your browser, and you can Google for that, and it's pretty easy to do. Probably should have showed you that how to do that, but it's pretty easy. Just Google, if you say clear cookies, how to clear cookies in your browser. Okay. But like it's a way of tracking you. Okay. And again, sometimes being tracked is good, sometimes being tracked is bad. So let's go to the next level. Not only do I want security, which means securing the information so people don't see it, I want my identity not even visible on the internet, so people don't even know that I'm visiting a site and so on. That is really hard, because that source IP address, that's your IP address, when you go to a site, it's logged. I showed you that with my server. It gets logged. The destination IP address, that gets logged. Okay, the DNS requests, they get logged. All this stuff is getting logged. The cookies are there, and so a server on the other side can say, can I see that cookie of yours? Who are you again? Let me see that cookie. And your browser's kind of doesn't know, and it will show the cookie. Okay, well, imagine that there is a system out on the internet which hides your source IP address from the remote site. Okay, and also hides destination IP addresses from the internet itself. Okay, so like a router on the internet doesn't, the destination IP address, but the routers on the internet don't know the source and destination IP address. They don't know the contents because they've encrypted. The DNS requests are done internally within the system so that the DNS servers don't see the requests. Cookies are scrubbed in a very intelligent way. You're going, wow, that's really hardcore. And yeah, that's what the Tor project was about. It was actually started by the U.S. military, by DARPA, and when people first saw this, they go, well, is this even legal? And yeah, of course it is, because just because it's a technology which gives you anonymity doesn't mean you're going to do something bad with that technology. You shouldn't do something bad with this technology. You just might want to hide your tracks so that like some company doesn't know what you're shopping for. Okay, so anyhow, because companies are notorious for businesses are notorious for wanting to get all this information on you. And so there's the Tor browser. Okay, remember that that's torproject.org. And basically the way it works is it does layer upon layer upon layer of encryption. It's actually 3 layers of encryption. And it doesn't pass it between any old routers. It passes it between what are called the onion routers. Okay, these special routers that'll peel off layers of encryption and then put these layers of encryption back on. And I did describe it, but I'm not going to expect you to reproduce that description because it's a little bit deep. Okay, and so by this technique of multiple layers of encryption, you can actually get a system where the routers on the internet, they don't know the source IP address, they don't know the destination IP address, and yet they can still get the packet to their final destination. You go, how is that even possible? That doesn't make sense. How can you get a packet to the final destination if you don't know where it's going? Because the final destination is inside one of the encrypted layers. And when it needs to get to that final destination address, it has the ability to decrypt that layer and get that. But it doesn't get all the information at once. Okay, so it gets only pieces of information at a time. The Tor system will only get a little piece of information at a time so that no one router knows where things are going. It's very ingenious, okay? And I failed to mention that you can also get it for Android. I don't think it exists for Macs. It's called TorFox. TorFox. Okay, so if you go on the Google Store and you get TorFox, you get the Tor browser on your phone. Okay, so there you go. There's full anonymity, and beyond Tor, I don't know of anything that gives you any better level of anonymity. Okay, so that's it for the security and anonymity part of the internet. There were just two other technologies that I wanted to tell you about. That became new technologies that emerged out of the internet that you should probably know about. Okay, you may never use them, but you should know about Bitcoins. You should know about Bitcoins. Okay, so to understand this technology, you have to understand two different ways in which services or files are shared on the internet. Okay, so when I say a file, when you're browsing the internet, and you go to a web page, those are actually a bunch of images that come down. Each image is a file. Okay, and so there's a server that's serving those files to your computer. Your computer is kind of like, when you go into a store, you ask the salespeople there to serve you. To ask, you say, look, I'm shopping for shoes. Show me shoes. Okay, so it's the same thing. Your browser goes to Google.com and says, send me this web page, and then Google.com sends that web page. Okay, so this is the server-client model, where there's a central server that is responsible for serving out the file or files, or serving out the service. Okay, whatever the service might be. All right, the service might be something like when you register for your courses. Okay, during registration. Okay, so when you go to, that's a service. You go to a website, and that's a central server that's serving you not a file, but serving you a service. Okay, so there's one central server, and then there are many clients, and they all go to this one central server. Okay, so this is very easy to set up, and most of the internet is server client, but it has a drawback. If the file or files become popular, that central server becomes more and more loaded. So the more popular the file is, the more loaded the server is, until the server can't serve all the clients. Okay, it's kind of like the popularity of the service or file undermines your ability to get that service out. Okay, the other problem is, of course, the power might go off on that server, or the server might crash for whatever reason, and then the service is offline. Okay, so it's a single point of failure, as it's called. Okay, so server client is good, but it has this fallback that it has a central point that can get either overburdened or fail. Okay, so there's another way of sharing files or services, and it's known as peer-to-peer. And the way peer-to-peer works, we'll talk about in terms of files, but you can do this with services too. Peer-to-peer, it takes a file that you want to share, especially a big file, and it chops it up into a lot of pieces. It being like whoever the original peer is, because someone's got to start this process going. Takes the whole file and chops it into a bunch of little pieces. It could be even thousands of pieces. Okay, when another peer comes and says, give me the file, it doesn't give the whole file to them. It just gives it one piece. And then it gives another piece to someone else, and another piece to someone else, and another piece to someone. Now, it's not the whole file that's going around this peer-to-peer network. It's just pieces. And what these peers are doing is they might say something like, look, I have piece number 500, but I need piece 501. And so someone that has piece 500 says, here's piece 500. And but give me piece 501. Okay, and so they exchange the pieces rather than the whole file, and so there's no one central server that's serving out the whole file. Each peer is serving out whatever part of the file it already has and asking for the rest of it. So each peer starts off as what's known as a leecher, which it's just like kind of pulling in as many pieces as it can. But then once it's got a few pieces, it can start to give those pieces out to others that don't have it. And before you know it, the leecher has a part of the file, and then eventually when it has the whole full file, it can serve out any piece of the file. Now it's known as a seeder, and it takes the pieces, it puts them all together, and it has the file. Okay, so it basically decentralizes the load. There's no one single center, no one single server that has all of the load on it. Rather, it's each peer is simultaneously uploading and downloading pieces of the file. Okay, and there you go. This is how peer-to-peer works. Okay, the advantage of peer-to-peer over a server client, no central point, and not only that, but the more peers there are, the faster the exchange goes. So it's the opposite. The more popular the file becomes in server client, the worse it is because the server gets burdened. Whereas in peer-to-peer, the more popular the file is, the easier it is because the more peers there are, the faster the exchange. Okay, so it scales in the opposite direction. All right. So there you go. Now, an example of peer-to-peer is BitTorrent. Okay, and BitTorrent is used for piracy, but it's used totally legitimately. So you should know about BitTorrent. And if you wanted to download a file and I just picked a generic name, something like called x.txt. Okay, well, you don't download x.txt. That's kind of the point. It could be a huge file. You don't download it directly. Rather, what you download is a tiny file called x.txt.torrent. That .torrent ending, okay, says I'm the file that can tell your browser or whatever BitTorrent client you're using. I can tell you how to get into the network. Okay, so this file here, it tells your browser who the other peers are. Okay, it's not the file, but it's the file that allows you to get into the network, and it's small, very small. Once you're into the network and you start asking peers, do you know of other peers? And then other peers will tell them about other peers and so on. You get into this network, then you start to do this exchange that I just mentioned a minute ago. Okay, so the .torrent file gets you into the network, but the file that you're actually downloading it's the same name, but without the .torrent ending. Okay, so the file you want to get is called x.txt, but the file that gets you into the network is called x.txt.torrent. Okay, and there it is. All right, and very robust. Okay, now I mentioned that it's used by in piracy. Piracy just means downloading like copyrighted material that you shouldn't be downloading, and because it belongs to like some company that doesn't want it shared on the internet. Okay, now that doesn't mean that like BitTorrent isn't used totally legitimately. Like it's an excellent way of say downloading. Remember, I downloaded that ISO. Okay, the Ubuntu ISOs. It downloads very fast for the reasons I mentioned. So it's totally legitimate. But pirates like this, not because it gives them anonymity. There's absolutely no anonymity in BitTorrent, which kind of surprises people. Okay, so anyone that's using BitTorrent, your IP address is totally exposed. Okay, so you say, well, why do these pirates love using it? It's because it's super robust. There's no central server that you can shut off and then the file isn't exchanged. You'd have to shut off every single peer before you can even possibly stop this file from being exchanged. And how do you do that if there are hundreds of people sharing some movie, some Disney movie, and Disney wants to stop them? There's hundreds of people sharing this. How do you stop them? You'd have to call every one of them and say stop it. And some of these are they're in Europe, they're in Africa. Like these networks, these peer-to-peer networks that are distributed all over the world, most of them will just ignore it. They'll just say, well, I don't care. This American company is coming after me. Oh, that's nice. And so it's almost impossible to stop. So BitTorrent is very popular among pirates for this reason, not for the anonymity. Their IP address is exposed, but for the robustness. And the thing is that I'll tell you, I'm not suggesting you do this, but a lot of companies kind of give up because it's just overwhelming to try to trace everyone down. Okay, so there you go. There's the story with BitTorrent. Maybe one more thing. A lot of browsers are capable of doing BitTorrent. Not all. Okay, so if your browser is not capable of doing BitTorrent, it'll save the BitTorrent, the torrent file to your desktop. Then you have to open up the torrent file in a BitTorrent client. Okay, and they're all over the internet. And when you double click a file and your computer doesn't know what to do, the operating system doesn't know what to do with it, it'll suggest to you some programs that might start it up. Okay, and basically you just download and install the BitTorrent client, and then you can open up these torrent files and start doing BitTorrent through that. Okay. All right, but a lot of browsers will just do it. So as far as you're concerned, you don't even know that you're using BitTorrent. You just click on it, and the browser says, "Do you want to do BitTorrent?" Because that's what my browser did. If you remember when I demonstrated this, do you want to do BitTorrent? You go, "Yeah," and it'll start doing it for you. Okay. Well, the last thing, and probably the most interesting of all the different things that the internet has given rise to, is a new type of currency. Okay, so don't think of cryptocurrency as just digital currency, because US dollars are digital. I mean, very few people now will actually carry paper cash in their pockets. You use credit cards or debit cards when you go to the store and buy things, even for small, even for like $5 or something like that. You'll use your credit card. Okay, no, it's not the digital part. It's how the money is created. Okay, so you say, well, what do you mean money is created? Well, someone gets to print money. Someone gets to do that. Now, if you print US dollars, it's called counterfeiting money, okay, and you get to thrown in jail. But there's some people that are allowed to print money, and that's the Federal Reserve in the United States, some centralized bank, okay. So most countries have some centralized bank that's allowed to print money. Now, when you print money, what happens is that you flood the, if you print a lot of it, you start to flood the market with money. It devalues the money. Okay, that's what inflation is. Okay, and we're actually undergoing 5% inflation right now. It's terrible. Okay, 5% doesn't sound like a lot, but in 10 years, that means that your money's worth half as much, or even less. So yeah, 5% will catch up to you. Okay, and the way that happens is by printing U.S. dollars. Okay, and so if you can get US dollars easily because there's so many of them in circulation, it means that they're not quite worth as much. Okay, and so cryptocurrency doesn't work that way. You can't just print bitcoins. You say, well, how do bitcoins get created? They're created by the solutions of these cryptographic puzzles. Okay, or cryptographic problems. And you go, what does that even mean? It means that these are difficult problems. Computers try to solve these cryptographic problems over and over and over again. And once in a while, one of them strikes gold. Okay, and it solves it. This striking gold is actually kind of important because what it means is that the solution are rare and difficult to find, kind of like mining for gold, which is why this process is called mining. But it basically takes the creation of the bitcoins out of the hands of some central bank or some central government and distributes the creation of bitcoins among random computers that are doing mining out on the internet. Okay, and so there's no control over the flow. There is a creation, but the creation is random. The creation of bitcoins is random by luck, by the solution of these cryptographic puzzles. And it's more like the old gold standard where, gold, you had to go out and mine gold out of the ground, and maybe you struck it rich, maybe you didn't. So there are these people that are running mining rigs and Bitcoin mining rigs, and every once in a while they strike gold. Well, they strike Bitcoins, and then they make a lot of money doing that, okay? And that's how the Bitcoins are created. By taking that control out of the hands of by taking the control of the creation of bitcoins and the money out of the hands of the government and banks and putting it into the hands of the people makes it a very different type of currency. Okay, and people who have certain types of political leanings or economic leanings, like libertarians, love this. Okay, my opinion is that the government will regulate anything. So look out, in the future, bitcoins are going to be more and more regulated, and so they'll kind of destroy that kind of Wild West sense to them. But that's the difference between bitcoins and fiat currency. Fiat currencies can be created by a central bank. Cryptocurrency isn't. It's created at random, and that makes a big difference. Okay, you can't inflate bitcoins. You can't go one day. Someone can't say, you know what, I'm going to create a whole bunch of bitcoins today and destroy the Bitcoin market by inflating bitcoins. Can't happen. Okay, can't happen. All right. So, but they can with U.S. dollars. So there you go. All right. Now, having said that, how do you use these bitcoins? Like where are they? How do you use them? Well, first of all, where are they? You can have them on a Bitcoin wallet. It's just a program that holds bitcoins, and you can use them. You can Google for like Bitcoin wallet. Okay, you can buy and sell stuff with them. Okay, you can store money, like you can store value, like like a savings account. Okay, and you can mine for them. Okay, nowadays most people are not using Bitcoin to buy and sell stuff. Bitcoins are mostly being used as kind of like a savings account. There are other cryptocurrencies. Bitcoin is not the only one. There's also like Litecoins, there's also Monero, there's also Ethereum. These are all different types of Bitcoins. And some of them are very much, they're better at being used to buy and sell stuff, okay? Bitcoins, it takes too long for the transactions to occur, okay? And that's what's going on, all right? And so all of these types of cryptocurrencies have this feature that they just can't be created by some central authority. Okay, and there it is. There's a lot more to cryptocurrency. I'm just giving you a very little taste of it, but it's important that you know about this because it may change the future of our economic system, and so you want to have some idea about how they work. Okay, you could read the Wikipedia page on bitcoins, and you get a lot more information. Actually, on cryptocurrency, you get a lot more information, and there are different types and so on. Okay, so there it is. in about what was it, an hour and 45 minutes, I've summarized everything that's on the test. Okay, so now go through this video, look at my summaries that I have, and when the test comes, it is open book, so you should be able to answer most of the questions right away. And if you can't remember the answers, you can refer back to the notes. Okay, but do study, because there's a lot of information, and if you're totally clueless about some subject, and I ask you a question about that, you're going to be spending a lot of time just like looking through those summaries, trying to figure out what answers the question. So have a clue, and then revert back to the notes during the test if you're really stumped on some detail. But spend some time studying. Okay, let me see if there's anyone in the chat. And no, no one showed up. Again, not a problem, but I hope everyone watches this before the test. Okay.